Bismillahirrahmanirrahim. Assalamu alaikum students. Now in last lecture we discussed the properties of vectors. Today we'll start with the idea of components of vectors. Components of vectors. Now, you know, if we have two vectors A and B, we can graphically find their resultant this way. We'll place the tail of B on the tip of A, then the vector pointing from the tail of A, the tip of B represents A plus B, right? Then this is called triangle of vectors. And there is another thing. If I have three vectors, vector A, vector B, and vector C, you want to find the resultant, you place resultant means the sum of these vectors, right? You place the tail of B on tip of A, then tail of C on tip of B, and you do that, you cannot disturb the direction or magnitude of the vector. Then the vector pointing from the tail of A to the tip of C is A plus B plus C, right? This is called polygon law vectors. Polygon law vectors. And this is true for any number of vectors. If you have 10 vectors, you place them this way. That means you place the tail of second on tip of first, then tail of third on tip of second, and continue this way. Then the vectors starting from the tail of first and ending at the tip of last vector will give you the resultant of those vectors. So this is polygon law of vectors. Now, vectors can be in two dimensions. That means vectors can be in plane, vectors can be in space, vectors can be three-dimensional. When we have to represent three-dimensional vectors graphically on two-dimensional page, it is a bit inconvenient because when we show angle between the vectors which are three-dimensional in nature on the two-dimensional page or board, right? Those angles do not appear, the angles which they are in actuality, because of the two-dimensional nature of the plane or page. Rectangles are something else, they appear something else, right? So to overcome this inconvenience, we have another way of adding vectors. We resolve vectors. We find components of vectors. See what we do. Let this be my xy plane, my coordinate system. We will consider two-dimensional vectors. So this my x, this y, this negative x, and this is negative y. Suppose I have a vector A. Let A be my vector. Now what I do, I know this vector has a magnitude, this vector has a direction. The magnitude is indicated by the length of the arrow, we know, and we represent that this way. This is magnitude of A. And how we specify the direction? Direction is indicated by this angle that we call this angle phi. We see angle with the positive x-axis but measured in counterclockwise sense, not this angle. We see this angle. There is convention. When we refer to angle of the vector with respect to our coordinate system, we have to see the angle with the positive x-axis measured in counterclockwise sense. So this phi denotes the direction of A, right? So we say that if vector is in 2 dimensions, it has magnitude, it has direction. Magnitude indicated by one number, because ultimately this magnitude will have a value. This phi will have a value. So we say in 2 dimensions, there are two numbers corresponding to a vector. Two numbers corresponding to a vector. One number indicates the magnitude and another number indicates the direction. And in 3 dimensions, there are 3 numbers corresponding to a vector. There also vector has a magnitude and direction, but in 3 dimensions, to specify the direction, we need 2 angles. So this is in 2 dimensions, right? But in 3 dimensions, corresponding to each vector, there are 3 numbers. One number specifies its magnitude and other 2 specify the direction, right? Now, what is the meaning of component? See what we do. When we have a vector, this place it in this coordinate system this way, we draw perpendicular from the tip of the vector on the x-axis and y-axis. Now this length, right? This length, that means the length starting from the tail of the vector to the foot of perpendicular on the x-axis. This length I write as ax. It is called x component of this vector. And this length is represented by a subscript y, right? So ax is called x component of a, x component of vector a, and ay is called y component of a, right? And this process of splitting this vector into these components is called resolution of vectors. Resolution of vectors, right? Now I have a vector A. It has magnitude, it has direction, 2 numbers specified in 2 dimensions. If I change phi, vector will change. If I change its magnitude, vector will change. I'm saying I draw perpendicular from its tip on x-axis and y-axis. Then this length, sometimes it is called x projection of A. This is called the y projection of A. These lengths are called rectangular components of A. Because this coordinate system is called rectangular or Cartesian coordinate system, right? So see, there is a relation between the magnitude and these components. See how. If this is ax, this is also ax, and this is also ay. This length is also ay. So I have this right angular triangle. I can use Pythagoras theorem. I can write magnitude of A is under root ax square plus ay square. This is my first. See how. Base square plus perpendicular square will give me hypotenuse square. Then the value of hypotenuse, that is the magnitude of A, is square root of ax square plus ay square. Similarly, I can write tan phi is ay by ax. So I can write tan phi is ay by x, right? Tan phi is perpendicular by base, right? So see, I said corresponding to a vector in 2 dimensions, there are two numbers. Magnitude and direction is specified by phi. Now I have another interpretation using components. Now I can say corresponding to a vector in 2 dimensions, there are two rectangular components. These are also two numbers. So these are two ways of specifying the vector. One is in terms of its length and angle, these two numbers. Second is in terms of its rectangular components, ax and ay. Similarly, in 3 dimensions, I said there are three numbers corresponding to a vector. One gives magnitude and two other specify the direction. And in component method, there will be three components, ax, ay, and az, specifying the vector. Now, question is, if I know these two numbers, x and ay, can I find a and phi? That means these two numbers. That is possible through this equation. See, in these two equations, if I know the components of a vector ax and ay, I can find its magnitude and direction. So knowing components, I can find magnitude and direction, or I can say knowing these two numbers x and ay, I can find phi and a. Now, is reverse possible? If I know magnitude and direction, can I find components? That's also possible. See, if I define sine phi is what? Perpendicular by hypotenuse. Sine phi ay by a. It's ay by a. What is cos phi? Base by hypotenuse. Base is ax by a, right? That means ax is, let me write it here, ax is a cos phi and ay is a sine phi. Let this be my third and this be my fourth. So observe these equations, what they say. Now these two equations give us these two numbers, magnitude and direction phi, if I know the components. This is reverse. Here, if I know the magnitude and direction a and phi, I can find the rectangular component. So x is a cos phi, ay is a sine phi, right? Now, this vector here lies in first quadrant. Now you need to remember If there are three components of a vector, then there will be one more term here plus az square in the magnitude, and you have to find another angle theta that will have another relationship, right? We are talking of two dimensions. Now this vector lies in first quadrant. This quadrant first, you know, this is second quadrant, this is third quadrant, and this is fourth quadrant. Now you see this vector lies in first quadrant, so its rectangular components are both positive. A phi, ax is positive, ay is positive. The vector lies in second quadrant. For example, let b be some vector, and if it lies in, let this see x, x dash, y, y prime, let b be a vector in second quadrant, then this is its angle, right? Its x component is, you have to draw projection. Let me create it first. Then I have to select this color first. Then I will select this color. Now I draw perpendicular on y, perpendicular on x. So this length is bx, and this length is by. See, vector b lies in second quadrant. Its x component is negative. Its y component is positive. I can have a vector y, y prime, x, x prime. So let it be a vector c which lies in third quadrant. Then this is its angle phi. The components are, you draw perpendiculars like this. This length is cx, and this length is cy. This length is cy. So see, this vector c lies in third quadrant. Its x component is negative, y is also negative. I can have a vector in fourth quadrant. My x, x prime, y, y prime. Let there be some vector d which lies in fourth quadrant. Then which is angle? This angle is the angle phi. And you draw the perpendicular on x-axis and y-axis, right? So this length is your dy, and this length is your dx. So see, if vector lies in fourth quadrant, its x component is positive, y is negative. So components are just lengths. They can be positive, they can be negative, they are scalars, right? So see, I can say if phi is between 0 and 90, vector lies in first quadrant, its x and y both are positive. If phi is between 90 and 180, then vector lies in second quadrant, its x component is negative, y is positive. Similarly, if a vector c lies in third quadrant, then phi will be greater than 180, less than 270, and its x component will be negative, y negative. And if phi is greater than 270, less than 360, it lies in fourth quadrant, x component of the vector is positive, y is negative, right? Then this was about the components. Every vector will have its components In 2 dimensions, it will have 2 components. In 3 dimensions, it will have 3 components, right? Now, we said, I want to first clear this. What is equality? We said 2 vectors are equal if their magnitudes are equal and they are similarly directed last time. Now, in terms of components, equality means 2 vectors are equal if all their components are equal. That means vector A is equal to vector B if and only if x component of A is equal to x component of B, y component of A is equal to y component of B. And if they are 3-dimensional vectors, then there will be one more component, z component of A is equal to z component of B. So equality in terms of component means all the corresponding components of the vectors are equal, right? Second thing, negative of vector. Negative of a vector. We said if we have a vector A, then what is minus A? The vector A is this, then minus A is a vector having same magnitude as A but oppositely directed. Now in terms of components, if vector A has components AX, AY, AZ, then negative of a vector has negative times components, all the components negative times. That means it will have minus AX, minus AY, minus AZ, right? This is the meaning of negative of a vector. Then we have another thing. Adding vectors using components, that is by component method, right? Let there be vector A, another vector B, and let S be the sum vector, the resultant. So S is equal to A plus B. Let they be 2-dimensional vectors. Before that, I need to clear one more thing. Last time we said that if this is X, this is Y, this is Z, then we have specified 3 symbols for 3 spatial unit vectors. You remember that I cap is a unit vector along positive X. J cap is a unit vector along positive Y, and K cap is a unit vector along positive Z. You know that. Now, if I have a vector with components AX, AY, and AZ, right? So when I have to write it in unit vector notation, we write it this way: AX I cap plus AY J cap plus AZ K cap. This is a way of writing a vector in unit vector notation. You can write any vector in unit vector notation. This is a 3-dimensional vector. If vector is in 2 dimensions, then it will have only 2 terms. For example, if it lies in xy plane, there will be only I and j term. If it lies in yz plane, there will be only j and k term. If it lies in xz plane, there will be only I and k term. So this is the way you know this. This is the way we write a vector in its unit vector notation. Now coming back to this sum, let there be a vector A and vector B and S be the resultant vector. Let they be two-dimensional vectors. So I write them in the unit vector notation. So this is x sx I cap plus sy j cap, and A is written as ax I cap plus ay j cap plus B is written as bx I cap plus by j cap. And then what we do next, I arrange it. I write this way: ax plus bx I cap. These two terms have I cap attached, so I take that outside the bracket and I can write it ay plus by j cap, right? So see, on left hand side I have a vector s. Sx is its component, sy is its y component, sx is its x component. On the right hand side, this whole thing is x component and this whole thing is y component. That means this vector is equal to sum of these vectors, means that this sx must be equal to x plus bx and this sy must be equal to ay and by. So means sx is ax plus bx and sy is ay plus by. Got it? Right? Now that means if you have to, if you add x component of a and b, you will get x component of resultant, and by adding y component of a and b, you will get y component of the resultant. Also we know magnitude of s will be under root sx square plus sy square. Now I can replace sx by ax plus bx square plus sy can be replaced by ay plus by. Then there is square, right? Similarly, I know tan phi, which gives me direction of s vector, will be sy by sx. Sy itself is ay plus by and ax sx is ax plus bx. So what is the conclusion? See, what is the conclusion? Conclusion is, if I am given two vectors and I have to find their resultant using component method. If I add the x component of a and b, I will get x component of the resultant. If I add y component of a and b, I will get y component of the resultant. And knowing the components of a and b, I can find the magnitude of the resultant using this relation. And knowing the components of a and b, I can find the direction of the resultant. This is how we add vectors using components of vectors using component method. This was my another thing. There's another thing called dot product. Dot product or scalar product. So I write here multi multiplication of two vectors to yield a scalar. So in vectors, we define an operation called dot product. We call it also scalar product because the resultant quantity is a scalar. Here we multiply two vectors and we get scalar as our product. What is the definition of this? So if I have two vectors A and B, which are non-zero vectors, that means the vectors which have certain length, then A dot B means magnitude of A into magnitude of B into cosine of the angle between the vectors. So if this is A, this is B, and there is angle phi between them, then A dot B means it is product of three things: magnitude of A, magnitude of B into cosine of the angle between the vectors, right? This is the definition. So, and remember, when you have to find the angle between the vectors, you have to join their tails and see the smaller angle, not this angle. This also rule in vectors. Join tails of the vectors. For example, if some vector C is this way and D is this way, this is not the angle between these vectors because here tip and tail joins. This is the angle between these vectors, right? So A dot B is magnitude of A, magnitude of B into cosine of the angle between the vectors. So magnitude of A is a number, magnitude of B is a number, cos phi is a number. So it is product of three numbers. That's why it is a scalar. That's why we call it a scalar product, right? We can write it, we can interpret it other way also. Now see what is B cos phi. Let me use another color, C. If you draw perpendicular from the tip of B on A and find this length, what is this length? This length is B cos phi, and it has a name. In vectors we call it component of B along A. Component of B along A. You can say A dot B is either product of three things: magnitude of A, magnitude of B into cosine of the angle between the vectors, or you can say it's product of two things: magnitude of A multiplied by B cos phi. You club into single entity, you call it component of B along A, right? Or you can do another thing. You can write it B into, there are three numbers, you can move them because product of numbers is commutative. You can write it B into A cos phi. Then the interpretation will be A dot B is product of magnitude of B into A cos phi will be what? Component of A along B. Got it? So I repeat it. A dot B is either the product of three things: magnitude of A, magnitude of B into cosine of the angle between the vectors, or I can write it product of two things: magnitude of A into B cos phi, and B cos phi is component of B along A, or I can write it magnitude of B into A cos phi. A cos phi will be component of A along B, right? Another thing, if which vector was my A? Another thing is first here angle between A and B is acute. Cos acute angle is positive. So here in this case, A dot B will be greater than 0, right? If angle between A and B is greater than 90 degree, like this is my phi. So in this case, A dot B will be negative, right? Because cos of obtuse angle is negative. So this product will be negative. Here it is positive, greater than 0. And if angle between A and B is Z, this is B, if angle between them is 90 degree, cos 90 is 0, then A dot B is 0. Now this thing is used as a test to check whether two vectors are at right angles or not. So remember, if two vectors are at right angles, their dot product is 0. So if you have to check whether two vectors are at right angles with each other or not, you have to find their dot product. If it turns out to be 0, from that you figure out that they are at right angles, right? Now I will give an example of dot product. In physics, we use dot product, and there are physical quantities which are themselves scalars and are expressed as dot product of two vectors. One example is work done by a constant force. Force is a vector. So when I say force is constant, that means its magnitude and direction both are constant during the displacement. So if this is my particle, it is its initial position, initial position. Now some force acts on it, represented by this arrow F. Now it displaces it to its final position. It is final position. Now this is my displacement vector S, and if during this displacement the force remains constant, right? This is the angle phi between force and displacement. Then by definition, if work done by this force is represented by W, it is expressed as dot product of force and displacement, F and S. Work is a scalar, force and displacement are vectors. So this is one example where we express a physical quantity using dot product. So work done by a constant force is defined as dot product of force and displacement vector. So all things related to dot product are applicable to work. That means it is magnitude of F, magnitude of S into cosine of the angle between the vectors, right? If phi is 90 degree, then work done by the force is 0, right? If phi is 0, cos 0 is 1, then work done by the force is simply product of force and distance traveled, right? Work can be negative if phi is greater than 90 degree. Work can be positive if phi is less than 90 degree, and 0 when phi is 90 degree. So all dot product rules are applicable to work, right? Now another thing, uh, I have already said that we have three spatial unit vectors, right? I cap is unit vector along positive x-axis, uh, j cap is unit vector along positive y, and k cap is unit vector along positive z direction, right? Now what is I dot I? If I find dot product of I cap with I cap, it is by definition magnitude of I into magnitude of I. The angle between I and I, they are similarly directed vectors, 0 cos 0 degree, which is 1. So magnitude of I is 1. 1 into 1 into 1 is 1. So I dot I is 1. Similarly, j dot j is also 1. And k dot k is also 1. So we can club these three things and write I dot I is equal to j dot j is equal to k dot k is equal to 1. So you need to remember this, right? Now what about I dot j, j dot k, and k dot I? See, it will be magnitude of I into magnitude of j into cos 90, because I is pointing along positive x, j is pointing along positive y, angle is 90, cos 90 is 0, so it will be 0. Similarly, j dot k will be 0, because j is along positive y, k is along positive z, angle is 90, k dot I will be also 0, because k is along positive z, I is along positive x. So I can club them and write, you can write I dot j is equal to j dot k is equal to k dot I, and all are 0. So remember this thing also. Y dot j is j dot k is k dot I is 0. So I will give you some homework now. Yes. So your homework is homework. It's a simple question. Question says, I will try figure. It is a figure. This is my vector A. Then I have vector B. Then I have vector C. Right? Now the length of A vector is 4. Length of B vector is 3 units. And length of C vector is 5 units. Here it is 90 degree. And in this figure 1. So question goes like this. Question says 3 vectors add to 0 as in figure 1. Or I write it this way, as in the right triangle of figure 1. Calculate part A, part B. Part B says calculate A dot B. Part B is calculate A dot C. And part C is B dot C. I repeat the question. 3 vectors A, B and C form a right angular triangle. This is my A, this is B, this is C. Length of A is 4 units, length of B is 3 units, and length of C is 5 units. This is a right triangle. The question says 3 vectors add to 0 as in the right triangle of figure 1. Calculate A dot B, A dot C, and B dot C. So this is all for today. Thank you. Thank you. God bless you. Do your homework. Don't waste your time. Assalamu alaikum.